Today we're going to begin moving into an understanding of integrals as area and start to get away from using Riemann sums to represent areas and move into the key fact that the area can be represented as an integral. And the integral is a fairly straightforward device that makes use of the fact that our Riemann sum here, if we let our total number of rectangles go to infinity and we have some relationship here, this represents the integral of the function f of x dx, or more precisely, the integral is a representation of this sum for functions in which the left-hand side exists. If a function does not have a good limit on the sum of these small rectangles, then we do not have an integral here. But this is the transition now, and this is our topic today, the transition from Riemann sums to integration, and we will try to focus on the key points that the AP test will make use of and ask you to apply, versus going through all of the nitty-gritty detail that you may not necessarily need to see for that test. So we'll start with the definition of the area under a curve. This is something that we have seen a little bit prior to this already. We will start with the definition of the area under a curve. If we go from some point A to some point B and we look at the area under that curve for our function f of x, we end up with what is called the definite integral. So the area under f of x from x equals a to x equals b is represented by the definite integral given by this expression, the integral from a to b of f of x dx. Now this is the area bounded by those objects there, the integral from a to b of f of x dx. And of course we have looked at a few examples of these integrals already as we have confirmed our results from Riemann sums, but I want to now talk about some properties of the definite integral. Some of these are definitions and some of these are ideas that we can sort of derive or show. All of these are very important for you to understand and be able to make use of as we go through and prepare for the AP test. Many problems on the AP test can be solved by knowing properties of integrals and applying those properties at the right time. First of all, one of the most important ideas we can have is one related to the order of integration. This is by definition the way that integrals are set up, but if we look at the integral from a to b of some function f of x dx, that will be the opposite of the integral from b to a of f of x dx. In other words, switching the limits of integration, switching them around, results in getting the opposite sign on your final answer. Very important one, frequently can be used to help simplify some problems, and is a good trick to be aware of. Another important idea, and this one is one that comes about from the fact that we can represent this as an area. If I take the integral from a to a of f of x dx, I will always get 0. In other words, if a is both the upper and the lower limits of my integration, the region of the plane that I'm measuring the area of is precisely 0. I'm not measuring the area of any region at all. This also has to be true, by the way, because of the first property we talked about, the order of integration. If the order of integration had that property and this was not the case, we would be in some big trouble here. Some more properties that we will be making use of later on. Just like with derivatives, we can worry about what happens if we have constant multiples in our integrals. So if I have the integral from a to b of some value k times f of x dx, if we multiply a function by a constant, or if there's a constant in there, we can factor that constant out, and the result is just k times the integral from a to b of f of x dx. So this is a very useful idea if we have constants that are not useful to us in the problem and we are able to factor those out. That becomes a very useful property as well. There's another property, a linearity property of derivatives. So we can look at addition and subtraction here as we did with derivatives. If I have the integral from a to b of some function f of x plus or minus some other function g of x, and we're integrating this whole thing. So this is like the sum and difference rules for derivatives. We can make the same kind of a claim. If I have a sum or a difference, as I do here, we can break this up into two pieces. So this can be expressed now as the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And so this is another tool for frequently breaking a difficult integral into smaller pieces, which we can attack one by one. Somebody had asked, I think Serafina had asked, about polynomials and what happens if we have a large polynomial that we're trying to find the integral of. Well, between the rule for multiples and the rules for sums and differences here, we can break a polynomial of any length up into individual terms, and we just have to be able to find the integration. We just have to be able to figure out what the result is there. Okay. Another important property of integrals is given by their additivity. We can combine, or also be aware we can cut apart integrals if we need to. If I have the integral that goes from a to b of f of x dx plus the integral that goes from b to c of that same function f of x dx, we can write this in a simpler way. Let's think about what these two integrals mean. The first integral says what is the area under the curve f of x from x equals a to x equals b. And the second one says what is the area under the curve f of x from b to c. So in reality what we're doing here is we're taking all of the area under the curve from a to c and we are adding those together. We're finding that total area. So this can be rewritten as the integral from a to c of f of x dx. And again, the important idea here, the important thing to make note of here is that the limit, the upper limit of one integrand is the same as the lower integration limit of the other one, and also that the function here and the function here are identical. And if those two conditions are met, we can combine these integrals together and be able to figure out what the result is there. Okay. The next property that I want to discuss with you is a property that allows us to estimate integrals. And this can be very handy in certain spots on the AP test. Sometimes you're actually asked to do this. Other times it can help you to narrow down your selection or narrow down what's going on with the answers. And this has to do with maximum and with minimum values. So I'm going to call, let's go ahead and call f max the maximum value of f of x on our interval from a to b. And let's call f min the same thing, the minimum value here. So the minimum value of f of x on this interval a, b. Now, assuming that our function has a nice integral, assuming that everything works out for us okay, one of the cool things that we can say here is that the integral from a to b of f of x dx has to be less than or equal to f max, the maximum value of the function, times the width of our expression. So think about that. What that says is that f maximum is the maximum height, b minus a is the width of our interval. So this goes back to thinking about this in terms of rectangle areas. This is the largest rectangle possible here. Okay. Likewise, our integral has to be greater than the minimum function value times the width of the interval. This is the smallest rectangle that would be produced by this function, and so our function has to be bounded by these two ideas. So we can often make use of this to help us solve problems, and that is the mean value theorem for definite integrals. This is a very useful and important tool as well. Mean value here basically just means the average. And the key idea here is that on some value or on some region from A to B, there has to be a point C such that the following condition holds, and that is that the value f of c is given by 1 over b minus a times the integral from a to b of f of x dx. And the best way to think about this is that this is simply saying that there exists a rectangle that we could choose, a rectangle on that interval that has the correct area, right? And maybe a better way to think about that is to rewrite this as f of c times b minus a has to equal the integral from a to b of f of x dx. So this is in some ways looking at things from a different perspective, but still talking about bounding the integral. If there was a maximum value that the integral could have and a minimum value that the integral could have, the actual value has to be somewhere in between there, and that somewhere in between value occurs when we pick just the right point in that function to give us one rectangle that actually has the same value. And this allows us to find that one point where we could have a rectangle that has the correct value for the area under that entire curve. So now we get to do a little bit of practice here in terms of using these rules to manipulate integrals and gain some familiarity with the language here. I'm going to ask us to go through on page 290 and do 1 through 15 odd. So page 290, please, 1 through 15 odd. That will be the assignment you will be working on in class on Monday, in addition to a small investigation to kind of motivate another important idea that I don't want to discuss right now, but we will be spending at least one more day on this material.